So first, just to kind of center us on where this is, this project is looking at the Calcasieu Ship Channel. That's where we focused in. You can see the Intracoastal Waterway here. This is the Gulf of Mexico. And this region of Louisiana there's a lot of economic activity, particularly because of the liquefied natural gas facilities. There's also chlorine plants in the region, which, if anyone has seen the price of bleach after the hurricanes in 2020, you'll have noticed, or if you have a pool, you'll notice that the cost of chlorine has gone way up because they got destroyed by the hurricanes. This region is also an extremely critical area for wildlife. It's one of the most important stopping points for migratory birds and the various wildlife refuges around this region. It's also eroding extremely quickly. The last time I checked, it was about 170 meters of erosion over a 10-year period. So that's about 55, 56 feet a year of coastal erosion. And so I mentioned that this was part of a larger project. And if we take a step back and look at the larger project and how we ended up at Calcasieu, we wanted to take one case study that had a long history of system modification, whether that's through placement to create islands or wetland placement, and accumulate all of the historical records of the dredging, the geomorphology of the area. Right now, Liz is working on numerical modeling to look at the historic dredge sediment placement strategies. So if you look at this right figure, to basin-wide scale to try to identify factors that are not necessarily in the model, but are still important and that might influence shoaling in that channel. And so you can see here, just a little bit more background on the study site here. Back in the 30s, pre the 1930s, you can see that this channel is not straight, came into Calcasieu Lake here, but smaller draft vessels, and then over time they've straightened it out, and it's now suitable for deep water shipping up to the port of Lake Charles. So looking at historical dredging rates, Rachel Payne did a ton of work on this, taking channel and dredging information from the annual reports, the Chief of Engineers, which is also known as the Chief's Reports, between 1874 to 1980. All that dredging information was cumulative dredging volumes, cumulative maintenance dredging volumes over time. And you can see right before late 1930s, you can see that they constructed that 30-foot channel. Mid 1950 or early 1950s, late 1940s, another deepening, and then 1960s, they deepened it once more. And this period here, that the hash bars represent a period of time where we are missing that data for the record. So looking at some of the previous work in the 7 budgets that have been done for this, for the shipping channel, Dave Perkey and a bunch of other folks here published a report in 2022 that looked at the volume of sediment as well as the percentage of the volume that they're having to dredge for a couple of different sources. You see that Calcasieu stuck out to me was this wetland erosion factor. And you can see the range in the uncertainty there, 10 to 38% potentially of the dredge volume from that channel is coming from wetland erosion. And you can see also that this number doesn't add up to 100. There's still a lot that we don't know about this system, and trying to account for where is the sediment coming from that we have to continuously dredge out this channel. Burdick, State Perky's group, their estimate was somewhere between 21 to 49% is unaccounted for, and the Water Institute also published a report recently putting that number even higher at 52 to 73%. So there's a lot we really don't know. And if you think about it, that uncertainty propagates forward to costing money in terms of understanding how the system works and maintaining that channel. And one quote from that report that I really like a lot is that there's no indication in any of the results that an engineering solution can be offered. There are no easy engineering solutions to reduce the shoaling in this region. And I like that a lot because a lot of the discussions and borderline arguments we've had in our team meetings when they come up are, there's so much that can go on in these systems. How do you pin down on one factor? And so to try to do that, we focused in on the wetland erosion side of things to try to better constrain this dredging volume and see if we can understand where that sediment's coming from. And so for wetland erosion, here's an overview map from a paper we did after the hurricanes in 2020. You can see, so this is 2004. If you look at this offshore point, by 2020, it wasn't offshore. Infrared, the top left corner of satellite imagery, you can see these borrow pits that were used to create a higher elevation area directly adjacent to it. So this region has been highly engineered. And so some of the major causes for erosion in Louisiana that are kind of commonly thrown out there are subsidence, which is deep geological subsidence or shallow, hurricanes destroying wetlands, and one that has quite a bit of attention on the eastern side of the state are oil and gas canals and production. I'm sorry, I don't know if y'all heard that. They're doing something with the AC here. Okay, so looking at that first factor, subsidence, a geological factor, and as a quick rundown of what kind of environment we're looking at, and to better understand how that could come into play. So you have reworked sediment being deposited, and as the river shifted back and forth, those sediment pulses were building up higher elevation regions of land. And because they were at higher elevations, oak trees would grow because they could tolerate the elevation better, and then you end up with the term cheniers. So in between those higher elevation ridges, you have lower elevation pieces of land where water and plant material would grow, decompose, and occasionally there'd also be more mineral-rich sediment from offshore from major storms. But as that material degraded over time, you ended up with a very highly organic, very soft material there. And those wetlands were traditionally lower salinity. And so this plot on the right, it's a little hard to see. I know the red on red here, but this is the outline of Louisiana. And I took the NOAA continually operating reference stations, which track vertical displacement over time. And you can see on the Mississippi River Delta Plain, which is really what most people associate with the Mississippi River Delta in Louisiana, much higher rates of subsidence because those sediments are much softer, they're much thicker there. Whereas in the Chenier Plain, you're looking at about half an inch, at most, a quarter of an inch, because that Holocene layer of soft compressive sediments is much thinner. So when you're thinking about subsidence, it could play a factor, but you wouldn't necessarily expect it to play as significant of a factor as on the eastern portion of the state. Another idea was hurricanes. This region has been struck multiple times through history with major storms, and it does cause significant shoreline retreat. So when you look at I mentioned earlier that the area was hit pretty hard in 2020. You had two major, one's a Category 4, Category 5 storms hit, essentially in the same spot in the same summer. So the other one, which we were just talking about, was oil and gas, canals, infrastructure. As you produce those fluids out of the ground, whether it's oil, gas, water, the ground can subside. So thinking about on the Delta Plain region, we'd expect that subsidence rate to be pretty high. And you can see in this region too, the main factor that I think would be causing issues with wetland degradation and then sediment suspension and transport into the river are these artificial canals that have been dredged through time. And when you zoom in, you can really see that this is not a natural structure by any means. You never see a perfectly soft marsh. It's really difficult. They've also done other ways you can do this is that you can dredge material out from these borrow pits and build an elevated access point. So you can see a well site here. You can see the outline of the pad that's already kind of degraded and the outline of the higher elevation region there. And that becomes more intense when you see the map of oil and gas wells just in that parish. So you can see, and it's difficult to even distinguish how many there are because of the pure number and the scale we're looking at here. But there's been a lot of oil and gas exploration and activity in the region. So if you think about each one of those wells, or a lot of these wells require modification of the system to act. That starts to add up quickly. And we're looking at a basin-wide effect. So to investigate those different factors and their importance on sediment and the volume that is needing to be dredged from the channel, we compiled all the data. I mentioned before, Rachel compiled all the chiefs reports. We access oil and gas records from the Louisiana Department of Natural Resources. They have a system called Sunrise, which is mandatory for all of their oil and gas companies to upload records. Now that's where our first major caveat comes from. There are oil and gas production records going back to the late 1970s that are digitized, and then before that they're called production cards, so handwritten, no cards that have been scanned. But the records for new wells and permits for those wells have been digitized all the way back. We also reached out to Brady Kumian. We have his land loss data and the model that he fitted to that data for the region. And we also have river discharge for the Calcasieu from USGS as well. So exploratory data analysis, just plotting up as an indicator, we have the number of wells, it extends the furthest back in time, the best temporal coverage we have. And the thinking there is, well, to drill these wells, we don't have direct records of how many canals they've dug or the dimensions of the canal or anything like that. But looking at the map of the wetlands, we know that they have to dredge these intricate canal systems, really modify the system. So we're using the number of wells here as a proxy for that activity, that modification to the system. And just plotting up an initial, just playing with the data, just looking at it firsthand. Team meeting, someone brought up spurious correlations of these time series. And so the whole idea there is when you have two time series that are trending over time, when you plot them up together, let's say you have two series that are increasing, it's always going to look like a correlation. If you have one increasing, they're going to look correlated. So this plot, I'm not so convinced it's spurious, but you can see the correlation between the per capita consumption of mozzarella cheese and civil engineering doctorates awarded. So to get around that spurious correlation and do a little bit of a deeper dive on this, we took Spearman's correlations for all the variables, which are great for non-uniform distributions, a little bit less sensitive to outliers. And then we did Granger causality testing. So just because the data are correlated doesn't necessarily mean that there's a correlation and causation, not necessarily required for one another, right? So the Granger causality testing was looking at, does one of these time series variables cause another? Cause there still needs to be some judgment applied, but it's a statistical metric for whether there's a relationship between time variables. And so processing for that analysis, the first thing we did was reinterpolate the data records, all of them, to 1-year intervals. And that's convenient because now doing the Granger analysis, when we input our time lags into the equation, they're now year-based. So we know 1 lag is 1 year, 2 lags is 2 years, which is very convenient. And you can see that with the interpolated data, I think visually it looks fine. It seems reasonable to use. To get out of that spurious correlation trap, we then took the percent change of these variables. So now we're not comparing just the overall trend of the data, we're looking at percent change year over year for each variable. And then for the hurricanes, because it's not happening every single year, and the records are not necessarily great, and in addition, there's been recent discussion that the category Simpson-Sapphire scale, I think is what you call it, might not necessarily be the best representation for the impact of these storms. We coded them in as a 0 for no hurricane and 1 for hurricane. So it's just a categorical on-off type switch to see if the striking of a hurricane in the region made a significant impact. And so first, I know this table is full, but we're just it's pretty strongly correlated to the cumulative gas and cumulative oil produced in the region. And it's very strongly negatively correlated to the land area. So as land area decreases, the volume dredged from the channel is increasing, which makes sense going back to some of the ideas from Dave Perky's paper, or his group's paper, that the wetland erosion is contributing pretty good percent to the volume getting dredged. We also see a decently strong correlation between the number of fields, so where they're drilling these wells, and then the actual number of wells. And interestingly, to me, the gas production really, really strongly negatively correlated with land area. So the more gas produced in this region, we're seeing a really strong connection to land area loss. But again, these correlations don't necessarily indicate that any of these variables caused another. So after doing the Spearman's correlations, we looked at the Granger causality test. And so this is a plot of the percent change for the number of wells, which are these orange circles, and the volume dredged, which are these red diamonds. And you can see visually it looks pretty close, right? And so when we look at these lags, we ran the Granger causality test. So if you think about what these lags are meaning is so that, if you looked at the number of wells in the year 1940, does that Granger cause is how you would say it, but does that cause does the number of wells in 1940 cause the volume dredged in 1942? Or for the 5-year period, 1940 to 1945, right? And what we found is that for the lags between years 2 what that would indicate to me is that they go out, you dredge these systems, you're altering the wetlands, and then over time, because those wetlands, that dredge material is placed in spoil banks, but you also now have hydraulic connections to the river, hydrologic connections to the river, and so you'll have salinity intrusion. So there's a 2 to 6 year period between when that activity first occurs to where we're seeing that sediment hit the canal, or the shipping channel anyway. And so kind of a theoretical framework for what we think is going on here. So they dredge the canals to get to the wells. And we'll go on the left side here first. So you place the sediment along the sides of that canal, creating spoil banks. And if you've ever been out in the wetlands in Louisiana, you can see these, they're everywhere. The wetlands are extremely flat, and then all of a sudden, spoil banks they're not necessarily always engineered. So if you think about, you have a pile of sediment on the side of the bank, they can be unstable and they collapse into the channel. So you have sediment being dumped into the channels. Those spoil banks also alter the surface drainage. So as water is on the wetland surface, now it's being altered by the presence of an extremely high elevation region. And those canals, or that sediment, what we're thinking happens is once they collapse into the canals, they're flush. And to get to the flushing portion, we go back up. So you dredge the canals. Those are forming hydrologic connections back to the river. So you have a freshwater system that now has a direct connection to salt water. So now you have salinity intrusion into these interior wetlands. That salinity is going to stress the vegetation. The wetland vegetation can only survive and is only productive in certain elevation and salinity ranges. So that vegetation dies off. When that vegetation dies off, the marsh loses sediment, the soil loses its integrity and collapses into ponds. And that sediment, again, is flushed. And interestingly, if we look at the left-hand side of that equation, when we went out for the hurricane season in 2020, we saw a difference in the amount of time it took for the wetland to be drained. So the wetland was flooded by the storm surge, and we had a transect that was protected by a breakwater and one that wasn't. And the breakwater protected transect was also the one that had the borrow pits in that first satellite image. I'm not sure if everyone remembers. So heavily engineered, had the higher elevation area directly adjacent to the borrow pits. That section of the area drained more slowly than the range which wasn't protected by that. So you're looking at a time difference of 4 to 8 hours, so if you think about these systems are being modified and they're affecting everything from a local scale, you've got vegetation at that one site elevation, to a basin scale where you have large scale inundation time period differences, right? And that's going to affect the vegetation and the soil properties as well. Looking at the right-hand side, in terms of marsh collapse, so this is a figure from a study we did on the opposite side of the state, but it conforms pretty well to the general theory of marsh. And what we found is that it lost a pretty significant amount of elevation. So you're looking at it's about 20 centimeters there, which doesn't sound like much, but when the whole coast is about 18 to 20 centimeters above sea level, it is pretty significant. And what we found is that these are age classifications, but essentially all you need to know is that over a long period of time, over 50 years, that elevation is never going to be recovered. And so that strength and integrity that the marsh has that it lost is never recovered because there's no sediment being delivered to these wetlands. And so what's interesting is when you look back at some of the older reports and some of the newer reports, older studies, newer reports, paleoecological data, looking at diatoms, flora, and stuff like that, shows that there was a rapid decrease in fresh vegetation in the region, just as oil and gas activity was spiking. So, there's the connections that allow saltwater intrusion. We know the wetlands are degrading and we're losing those wetlands in that region. But there's also, if you look at the diatoms in the region, we can see that there was a significant and rapid die-off of fresh vegetation in the system. So if you think about large-scale wetland loss, that sediment is now available to be flushed and put out into the channel. So, kind of conclude, I know we went a little bit quick, so hopefully we have a good discussion afterwards, but to conclude, there's a pretty strong statistical correlation between the number of wells and the volume that's being dredged out of this channel. In addition to the correlation, there's also a causation relationship. That we see that we have the cause and then we see the effect a couple years later. And I think what's also interesting is that this system is, you're almost seeing a positive or a negative. I always get those two confused in this kind of context, but a feedback loop where the closer you are to the coastline, your proximity to the coastline is going to affect tidal prisms and currents, which is going to change how these canals, these interior canals, get flushed. And so as that coastline erodes, now your distance in these interior wetlands is changing. It's going to directly affect the amount and how those channels are being flushed with that sediment. And in fact, a report in the 70s showed, or a paper in the 70s, that these canals could increase the discharge rates through them by over 100%. So it seems like the hydrologic network facilitates the salinity intrusion that kills off the vegetation, but it also provides a pathway for the now eroded sediment or ponded sediment to be flushed into the channel. And so, going back to what Dave Perky's group wrote in that paper, there's no easy solution here. But one that has been proposed in Louisiana, I'm not sure on the status of it, is plugging these canals. So you block the connectivity of them, right? And I think the numerical modeling that Liz is doing, and maybe in other ways too, might better help us understand that flushing process. And I just want to bring up as well before I finish up, one of the more interesting things I saw when we're looking back at how this system has changed because of these canals and the flushing. Apparently it's directly affected the behavior of alligators. So now you have warmer water. I don't remember exactly what it is, but the alligators now, their behaviors changed completely. So this system is being modified for energy extraction and shipping, right? And we're losing the wetlands, and we're also directly affecting the ecological function of these wetlands. So they knew that in the 40s and 50s, and now we have all these wildlife refuges. So there's a real importance to understand both financially in terms of maintaining the channel, looking into the future for different wetland placement strategies in the region, and also maintaining those wildlife refuges, which are some of the most important in the country. So with that, if anyone has any questions or comments, we'll love to talk about it.